Recently, Bloomberg News reported that thousands of servers across the United States are containing hardware Trojans inside. Companies affected range from Apple to Amazon, even the CIA. This alleged breach is massive, and it just so happens that my team, consisting of James Anders, computer engineer, Armand Appin, electrical engineer, and myself, Isaac Urcuyo, computer engineer, have been working on this very exact problem. The problem being an issue in the supply chain. When ICs or PCBs are designed and eventually manufactured overseas, nation states are able to infiltrate the supply chain, implementing malicious circuits known as hardware Trojans inside of those products. So my team, in the security world, there's research done to demonstrate vulnerabilities for the better good of the public. So my team set out to implement a hardware Trojan in a wireless network under the guidance of Dr. Subramani and Dr. McCree's of UT Dallas. Specifically, we were designing hardware Trojans in a software-defined radio platform using new radio, and this is implementing an 802.11ag protocol, and our Trojan specifically implements a covert channel. And a covert channel in a wireless network allows rogue data or rogue information to be transmitted within a legitimate signal. Ultimately, we accomplished our goal and have a contamination rate of 0.2%, which corresponds to a BPSK modulation encoding scheme. 0.2% would be about 12 kilobits of rogue data throughput per second. And ethics was a huge concern on our project just because of the nature of the material. But we, at all times, we're working in a secure lab environment supervised by professors, and we're not releasing our code. We are definitely not releasing the code, but are going to be using properly licensed and open source materials. And there's not enough time in 3 minutes for me to begin to explain the contents of the Trojan, how we did it, because this is a PhD level project. But I can say it dealt with forward error correction, which is uses the transmitter to generate redundancy bits so that the receiver can then auto-correct any bit flips that have occurred due to noise. It's a great feature, but it's a point of weakness in a sense, because we can exploit this by having an additional FEC block inside of the transmitter, which contains rogue data, which will be leaked and substituted inside of the legitimate signal without a trace. Because when the receiver sees those bit flips, it thinks they're just due to noise, not rogue information, auto-corrects them, and there's no harm done. And we performed an analysis of about 50 hours on the network using performance metrics such as the cyclic redundancy check and the signal to noise ratio, and our results indicate that it's extremely hard to detect this Trojan. And please come to our demo session later this afternoon where we can go much more details into how we implemented the Trojan and also give you a hands-on opportunity to use the live network itself.
So this device will detect the Trojan that's there.
So no, we set out to demonstrate the Trojan itself.
Okay. So you can show the problem, but you don't have a solution yet.
Correct.
Yes.
Okay.
Research in the security world is focused primarily on developing 0 days attacks. So 0 days are things that have not been patched yet, but
okay.
that does not mean that people out there are not using them. So if you have, like, let's say, an Apple iPhone and you have a vulnerability inside, you could have that vulnerability for years without knowing. But
right.
researchers like ourselves and our professors will find those vulnerabilities, make them public so that Apple says, oh, I see what's going on. Let's check and make sure that's not happening in our case. Otherwise, you would go years without knowing that thousands of servers across the United States had a hardware Trojan inside of them.
Okay.
So what's not clear to me from the slide that you've got here is what your goals were ahead of time. There's a concern in the industry about the various kinds of tampering that can be done in the manufacturing phase. But what was the goal of the research here? Was it to demonstrate a mechanism? And if so, I'm not quite clear how the contamination issue is basically like how much bandwidth you can generate
Yes.
in an existing network without
So the goal,
corrupting the existing.
my goal for this presentation was try and have you guys understand the problem, and I think I did so. The goal of the project is to demonstrate the vulnerability itself, to demonstrate that the Trojan is possible.
Really just bring awareness to this specific type of instance of a hardware Trojan, but hardware Trojans in general, really.
Yeah, our professor actually, this is a PhD level project, they did a similar Trojan that had a 2% contamination rate, but ours is even more inconspicuous at a 0.2% contamination rate.
Okay. What's not clear is how that, if the normal forward error correction is going to filter that out anyway, how you get that further into the system where it could
Okay,
actually do
I
damage.
I see what your problem is, or your misunderstanding, or my not conveying it correctly.
Please, go ahead.
The receiver, if I'm sending something to you, totally legitimate communication, your autocorrection will handle that, and you'll receive the message I intended. But someone else has a rogue receiver, since it's a wireless network, they are still receiving that signal. There is rogue messages, rogue data inside that signal that they decode differently through a Viterbi decoder, which we also designed. So there's a rogue receiver as well. I should
So
mention that.
is a bottom line, if somebody sends you guys a box, you can find out if you can hack it or not?
We were not setting out to try to detect it. We were trying to demonstrate it's possible.
Right, so if manufacturer says, I got this hack-proof box, and you guys say, give me a week, and we'll see what we can do and demonstrate whether you can or can't.
That would be the goal. We're
Okay.
trying to demonstrate it, show that's possible. And this graph is showing different encoding schemes, BPSK and QPSK. You'll notice how similar those plots are. That's a legitimate network and the Trojan network side by side at such gains and error rates. So at error rates of 1%, which is, or 0.01%, then you're having identical networks. You cannot detect this.
Wow.